Good morning everyone, Mr. Ish over here. Thank you for joining me for this video. Today is a video more of an intellectual curiosity or something of an intellectual interest versus presenting a formalized topic. It's a topic of precalculus, Euler's number, abbreviated with that symbol E. You know in layman's terms that E is also called a natural exponential base. You've seen it before. Log base E, synonymous with natural log. This Euler's number. If you put number 1 in your scientific calculator, then you hit the shift button, and then you hit that button which looks like this natural log e to the x. It gives you the value of e to the 1, which is also equal to e, and it'll tell you very well what this number is. It's an irrational number, but it looks something like 2.71828 repeating in an infinite character with a non-reproducible pattern, which means it's a patternless number continuing on forever. It's an irrational number. And that irrational number is the Euler's number. I want to present this video, short video, just to present some interesting points with regards to this number. Interesting facts related to this number E arise because of the inverse relationship between this e to the x. Both of these functions, the natural log and the exponential functions, are inverses of one another, and you can come up with very interesting facts with regards to that e, the natural exponential base, some of which I'll present right over here. Anytime you see anything of this fact, natural log e to the x, it'll always equal to x. Likewise, anytime you see anything e to the minus x, it'll always equal minus x. For example, a question of this first character right over here can be natural log, you're doing e cubed, you'll equal 3. And how about this natural log e to the minus 3, you'll get minus 3. Reason being, looking at the first case, natural log e to the x, natural log e to the x, you can just write as this, e to the x. This x can come out over here using the properties of logarithms. You end up having x natural log e, the natural log e equals 1, so you hence have this expression equal to x. Here x was a 3, therefore it equal to 3. When you look at this other case, natural log e to the minus x, you can again bring this minus x over here. You have a minus x and you have a natural log e, hence you get a minus x. Another way you can also look at this secondary relationship right over here. Relationship is natural log e to the minus x is also the same thing as looking at natural log 1 over e to the x. You can use properties of logarithms. You can write natural log 1 minus natural log e to the x. You remember this. Anytime you have logs and you have a divide, common logs with divide, the divide is a difference of the two expressions, whereas a plus sign is a product of two expressions. Natural log 1 is equal to 0, hence you're just looking at 0 minus natural log e to the x, which is exactly the first relationship, which you know is equal to x. 0 minus x, and you get minus x. And you can see this same outcome arising from this expression right here, looking at it in two ways. Way number 1, way number 2. By eliminating the negative exponent and making it into a reciprocal, or let's just say you can arrive at the same outcome. Let me show you two other interesting relationships. This Euler's number also comes into these other interesting relationships. The natural exponential base, by virtue of its inverse relationship with natural log x. See this. Anytime you see anything which looks like this, e to the power of ln x, you know automatically it's equal to x. I'll show you. Anytime you see something which looks like e to the minus ln x, you have 1 over x. Examples. E to the ln 5 will equal 5. E to the minus ln 5 will equal 1 over 5. Let's show you how these play out. Looking at the first case right over here, e to the ln x. Imagine y is equal to e to the ln x. Eliminate this exponent by invoking the logs. Natural log. Natural log y is equal to natural log x ln e, which becomes a 1. Take everything onto one side. Ln y minus ln x is equal to 0. Under a common log, you have ln y over x is equal to 0. Take the natural log on the other side. Y over x is equal to e to the 0, which is equal to 1. Therefore, y is equal to x. Y was originally e to the ln x. If y is equal to x, then e to the ln x is equal to x. And you see it right over here. Let's look at the second relationship. Y is equal to e to the minus ln x. Use the properties of logarithms. Ln y is equal to minus ln x, ln e. which is equal to 1. Take this onto the other side, ln y plus ln x is equal to 0. Use the properties of these common logs, ln yx is equal to 0. Take the natural log on the other side, yx is equal to e to the 0, which is equal to 1. Y is equal to, take x on the other side, 1 over x. So you can see if y is equal to e to the minus ln x, which is equal to 1 over x, you see the 1 over x very well proving this part right over here. So anytime you see some expression which looks like this, the e's and the natural logs will cancel out. Here, in this case, the e's and the natural logs will cancel out, but you'll get the reciprocal of that number, which is being affected by the natural log. You see the Euler's number play out in a very important limit. Limit as x approaches 0, e to the x minus 1 over x. And you have to determine what this limit is, and you'll always find this limit to equal 1. You could use a calculator and use right and left side approximations. From the right side you could do 0.001, from the left side you can do minus 0.001. Plug them here in places of x's and you'll always come back at 1. But I want to show you this in another way, perhaps a more interesting way. This interesting way arises in the following way. If you say let y equal e to the x minus 1, and you take this 1 on the other side, you have y plus 1 is equal to e to the x. You solve for x here. Ln y plus 1 is equal to x ln e, which is equal to 1. Therefore x is equal to ln y plus 1. Within this part over here, we've come up at two substitutions we can place into this function here on the top. One substitution is this. The other substitution is right over here. You see here in the numerator we have e to the x minus 1. Well, e to the x minus 1 is equal to y, so we can rewrite everything as limit y approaching 0. The numerator e to the x minus 1 is replaced by this y. This x is replaced by this here because x is equal to ln y plus 1. This numerator y can be brought down, and it should be brought down, and you can bring it down in the following way. Limit y approaching 0. This y can be looked at as 1 over y, natural log y plus 1. How does this y come down as 1 over y? Because if you do this 1 over y and you flip it around over a fraction, you know the fraction, when you divide a fraction you flip it and you multiply it, that's exactly what you're doing. 1 over y is equal to y. So y is equal to 1 over y, which is how that y came down from the numerator into the denominator as a reciprocal of that y. Now what you have to do, use the properties of logarithms and rewrite your expression as this. Limit as y approaches 0, 1 over natural log y plus 1 to the power of 1 over y. You see this 1 over y, it just transferred right over here. You know that the powers can transfer back and forth. And you can rewrite using the properties of limits. Your expression can become this: 1 over natural log limit y approaching 0. You have y plus 1 to the power of 1 over y. You have to address this part right over here, which is above this underline, and you solve that out. As you approach values close and close to 0, either from the right or the left, this little part will always become equal to, you can test it out. If you test it out with value like 0.001 and put it in there, you'll see there's a 1.001 to the power of that 1000. I end up getting 2.7169. As the values become closer and closer to 0, this expression right here, which is outside the natural log, but this expression will become closer and closer to e. In essence, what you end up having is 1 over natural log e, and you know natural log e is equal to 1 over 1, and then that's equal to 1, and that's how you show that this expression, which is a famous expression, a famous limit which involves the Euler's number, is always equal to 1. Graphically, the same expression that we just saw, if you were to graph it out, it would look something like this. Here's your function. At this point of intersection, you have a 0, 1. This expression right here is graphed that way. As you're approaching x, as x values are approaching 0 from the left, or x values are approaching 0 from the right, your function will always approach as 1, which is this right here. An interesting curiosity with regards to this in terms of how you can calculate this limit. So the previous limit that I showed you ended up towards the end having something play out this way. Of course I was doing that with regards to y. Here it's with regards to x. It doesn't matter. If you were to graph this and we showed you how something like this always equals e, you'd end up having an intercept over here. Your function would come down like this and it would go in that direction. And this intercept here would not be 0, 1, it would be 0, e. as x were to approach the values of 0 from the left, or x were to approach the values of 0 from the right. You're seeing these values from the left and from the right. You'd approach this value over here in terms of your range or your output, your function approaching the value of e, and you'd see this. Your takeaway should be these relationships which involve the Eulers. A number over here should be these. Anytime you see anything which looks like ln e to the x, you don't need to worry too much about calculations. It's equal to x. Ln e to the minus x, you know it's going to equal minus x. When you see e to the ln x, it's going to equal to just x. In e to the minus ln x here, you'll have 1 over x, and I've shown you how these arise. These are something for you to commit to memory because they can serve as excellent shortcuts. So let's close the video with this. The Euler's number, or more so this Euler's symbol, the exponential function to which it is very inherently attached and associated with, obtains most of its interesting points and aspects or attributes because of its relationship to the natural log. If y is equal to ln x, right, you can say x is equal to e to the y. Or how about this, if y is equal to natural log x, flip the letters around, x is equal to ln y, and then solve for y is equal to e to the x. So you're seeing over here y is equal to natural log x and y is equal to e to the x by means of this inverse relationship. The inverse relationship being very well demonstrated by the fact that the exponential function has an intercept at 0, 1, the natural log has an intercept at 1, 0, and they are good reflections across this imaginary y equals x line. Something that you've seen before in precalculus, but that's the inverse relationship between the two functions, exponential and natural log. And you know e is very well associated with the exponential and the natural log. It's very well associated with the natural log function simply by virtue of base e of a log is equal to or synonymous to natural log. So keep the e symbol in mind. You know it's a Euler's number equal to 2.71828, an irrational number, but it has very many interesting relationships with the natural log, and it comes up in terms of many interesting limits also. So I will stop the video with that and bid you all farewell. Thank you for watching. Have a good day.